A calculation I made in 1974 should have been routine. Just another afternoon in my Cambridge office where I held the Lucasian Professorship of Mathematics, the same position Isaac Newton once occupied. That calculation kept me awake for weeks because it revealed something that shouldn't be possible. And what I found was that black holes, the ultimate prisons of the cosmos, were leaking energy and slowly evaporating into nothing. My mathematics pointed to a crack in the foundation of physics itself, and 50 years later we still cannot identify which foundation has to break. The story everyone knows about black holes goes like this. Gravity crushes matter so completely that nothing escapes, not even light, and anything that falls in vanishes forever. That version sounds simple and final, but it left me troubled for years because an object that lets nothing escape should be completely invisible against the blackness of space. The Event Horizon Telescope answered part of that puzzle in 2019 when it captured the first photograph of a black hole, a shadow ringed with fire in the galaxy M87 some 55 million light-years from Earth. LIGO has detected their presence in a different way, picking up gravitational waves from colliding black holes, ripples in space-time that traveled a billion years to reach us. We find these objects everywhere we look, and that's when the simple story starts to fall apart. My serious work on black holes began in the early 1970s, and back then I accepted what everyone else believed. These objects functioned as cosmic vacuum cleaners, one-way doors leading to oblivion, the ultimate dead ends scattered throughout the universe. That belief turned out to be wrong, and discovering just how wrong meant I had to break physics apart and try fitting the pieces back together in a completely new arrangement. The real beginning of this story comes in 1915 when Albert Einstein published General Relativity, his theory explaining gravity as geometry. Space and time in Einstein's framework are not fixed backgrounds where physics happens, but dynamic and responsive, curving and warping whenever matter and energy are present. A massive object like the sun creates a dimple in the fabric of space-time, and planets follow the curves of that dimple the way a marble rolls along a curved surface, which is what we experience as gravity. Karl Schwarzschild found something strange in Einstein's equations within months of their publication, and he did this work while serving on the Russian front during World War I. An autoimmune disease was killing him, and he had perhaps weeks left to live, yet he spent those final days calculating what happens when enough mass gets compressed into a small enough space. His mathematics showed that space-time curvature would become so extreme it would fold completely inward, trapping light on paths that all lead to the center with no route outward. We call this boundary the Schwarzschild radius now, or the event horizon, and crossing it means entering a black hole. Physicists treated Schwarzschild's solution as a mathematical curiosity for decades because surely nature would never create such a monster. Einstein himself refused to believe these objects could actually form, but nature does not ask our permission. Stars eventually exhaust their nuclear fuel and begin to collapse, and Subramanian Chandrasekhar calculated in the 1930s that above a certain mass, nothing can stop that implosion. The matter crushes past the Schwarzschild radius and a black hole forms. Cygnus X1 became one of the first candidates we identified, and I made a famous bet with Kip Thorne against it being a real black hole, partly as insurance, so that if these objects turned out not to exist, I would at least win something. I lost that bet and paid up with a subscription to a magazine of his choosing, which turned out to be Penthouse, much to his wife's displeasure. My own contribution to this field came in the 1960s through collaboration with Roger Penrose, who would receive the Nobel Prize in 2020 for the work we did together. Our theorems proved that black holes were not just possible but inevitable consequences of Einstein's equations, and inside each one lies a singularity where space-time curvature becomes infinite and density loses all meaning. Physics breaks down completely at that point, which disturbed me enough on its own, but something else bothered me even more. Black holes appeared to violate the second law of thermodynamics, one of the most solid principles we know. Entropy, which measures disorder, always increases in any isolated system, and this is not just a tendency but appears to be an absolute rule. Ice melts in warm water and heat spreads from hot objects to cold, and the reverse never happens because scattered water molecules do not spontaneously organize themselves into ice cubes. The problem becomes clear when you imagine dropping a box of carefully measured gas into a black hole, where it crosses the event horizon and vanishes completely. Classical theory says black holes have no internal structure and no features beyond mass, charge, and spin, a condition we describe by saying they have no hair, which means they cannot store information about what fell into them. The entropy of that gas appears to simply disappear from the universe, and the second law appears violated. A young physicist named Jacob Bekenstein proposed something audacious at Princeton in 1972, suggesting that black holes do possess entropy, and that this entropy is proportional to the surface area of the event horizon. That idea struck me as absurd at first because entropy is supposed to be about counting microscopic arrangements, about how many ways you can shuffle atoms while keeping the same large-scale properties, and I could not see what the area of a mathematical boundary had to do with counting anything. I set out to prove Bekenstein wrong, and what I discovered instead changed everything I thought I understood. Understanding my discovery requires knowing something strange about empty space, which most people imagine as pure void and perfect nothingness. Quantum mechanics forbids that kind of emptiness, because Werner Heisenberg's uncertainty principle creates limits on how precisely we can know certain pairs of properties at the same time. Energy and time are linked in this way, and the more precisely you specify one, the more uncertain the other becomes, which means that even a perfect vacuum experiences constant energy fluctuations. Empty space operates like a dead economy, where particle pairs appear constantly, matter and antimatter together, borrowing energy from the vacuum, the way someone might write a check on an account that must balance to zero. The universe permits this overdraft for the briefest instant and then demands immediate repayment, at which point the particles annihilate each other and the energy returns, keeping the books balanced. These virtual particles normally leave no lasting trace because the debt always gets paid. The situation changes at the edge of a black hole, where a virtual particle pair might appear just outside the event horizon with one particle carrying positive energy and the other carrying negative energy. Normally they would recombine instantly and cancel out, but the overwhelming gravity of a black hole can pull one particle across the horizon while the other escapes. The negative energy particle falls inward and the black hole absorbs it, which decreases the black hole's mass, while the positive energy particle becomes real and carries energy out into the universe. One particle declares bankruptcy and falls in holding the debt while the other escapes with the cash, and this means the black hole radiates energy outward. That conclusion sounds impossible, because black holes are defined by nothing escaping their gravity, yet particles stream outward from an object that should trap everything streaming inward. My paper in Nature from 1974, titled Black Hole Explosions, with a question mark, made many physicists suspect I'd made an error somewhere in the calculation. Months of checking confirmed there was no error, and the universe turned out to be stranger than anyone had assumed. This radiation has a temperature that depends only on the black hole's mass, and I can give you the precise number for a black hole with the mass of our sun, which would be about 60 nanokelvin, or 60 billionths of a degree above absolute zero. That temperature falls far below the cosmic microwave background radiation left over from the Big Bang, which means such a black hole would absorb more energy from its surroundings than it emits and slowly grow over time. Smaller black holes behave very differently, and primordial black holes that might have formed in extreme conditions moments after the Big Bang could have the mass of a mountain compressed into a space smaller than an atomic nucleus. That kind of black hole would burn at billions of degrees and radiate energy at a furious rate, and as it radiates it loses mass, which makes it smaller, which makes it hotter, which accelerates the radiation further in a runaway process. The final moments of such a black hole would produce an explosion equal to 1,000,000 hydrogen bombs, a flash of gamma rays marking its death. Black holes evaporate and they are not eternal, which is what I explained in A Brief History of Time without using equations, because I wanted the ideas to reach people who would never read a physics paper. That book sold more copies than I ever expected, though I suspect many buyers never finished it. The central message remains simple. Given enough time, every black hole will radiate away its mass and disappear. Supermassive black holes containing billions of solar masses at the centers of galaxies will take an almost incomprehensible span of time to evaporate, roughly 10 to the power of 67 years for a black hole with the mass of our sun, which is a 1 followed by 67 zeros. The current age of the universe is only about 10 to the power of 10 years, which makes these timescales seem longer than eternity itself. But eventually every black hole will die. My discovery connected quantum mechanics and general relativity in a way nobody had managed before because the temperature and entropy of black holes emerged directly from combining Heisenberg's uncertainty with Einstein's curve. Space-time. Bekenstein turned out to be right about black hole entropy, but the reason runs deeper than either of us understood at first, and the entropy being proportional to the horizon area somehow counts quantum states in a way we still struggle to explain. The real trouble started with a question I accidentally created, a puzzle that has tormented physicists for 50 years and sparked what Leonard Susskind calls the black hole war. When something falls into a black hole, and the black hole eventually evaporates, we have to ask what happens to the information that object contained. Human DNA holds about 750 megabytes of data in billions of base pairs, encoding everything from eye color to disease susceptibility. And when a person dies, that information disperses into the environment, but physics says it never gets destroyed because it could, in principle, be reconstructed. The laws of physics run in both directions, and information is conserved. Dropping that DNA into a black hole changes everything because the black hole gains a small amount of mass and its horizon area grows, but no record remains of what fell in since black holes have no hair. Time passes, and the black hole radiates until it evaporates completely, but the radiation is thermal and random and carries no information about the DNA. The information that was a person appears to be erased from reality, not just dispersed, but deleted, with no copy remaining anywhere in the universe. That scenario violates something called unitarity, which is even more foundational than the second law of thermodynamics. And quantum mechanics requires that information never truly disappears, but only gets scrambled. Every physical process must be reversible in principle, even when practical reversal is impossible. And if black holes destroy information, then the foundations of quantum mechanics develop cracks. I argued for many years that black holes really do destroy information and that quantum mechanics itself needed modification, but many physicists disagreed with that position. Susskind mounted what he called a 30-year war against my argument, and John Preskill at Caltech bet me that information must somehow escape. Evidence from string theory and other approaches eventually persuaded me to reconsider my position, and in 2004 I conceded the bet and presented Preskill with a baseball encyclopedia to replace the information the black hole had supposedly destroyed. Honesty requires me to tell you that we still do not understand how information escapes from an evaporating black hole. The holographic principle suggests that all information inside a black hole is encoded on its two-dimensional surface, like a cosmic hard drive storing three-dimensional reality at its boundaries. And some neuroscientists wonder if consciousness works in a similar way, with experience encoded on the brain's surface and projected inward as the sensation of depth. Black holes might be teaching us something about minds as well as matter. Juan Maldacina's ADS, CFT correspondence from string theory supports this picture mathematically, and we have proposals involving wormholes and quantum entanglement, but a complete and satisfying physical answer remains out of reach. Many physicists now claim the paradox has been solved, but I am not fully convinced because we have achieved mathematical consistency rather than physical understanding. The honest answer reflecting where we actually stand is that we do not yet know how nature reconciles these principles, and the crack in the foundation remains visible. What I gave physics was not an answer, but a question that reveals how incomplete our understanding remains. General relativity and quantum mechanics have both passed every experimental test we can design, yet they cannot both be entirely correct in their current forms. Black holes and the birth of the universe are places where gravity becomes extreme and quantum effects matter. And our best theories contradict each other in exactly those situations, which means something foundational must eventually yield. That state of uncertainty is not failure, but the authentic condition of physics at its frontier, where we stand at the edge of knowledge genuinely unsure what lies beyond. Black holes are not just strange objects scattered through the cosmos, but laboratories where the universe shows us precisely where our theories break and invites us to discover something deeper. More than 50 years of my life went into thinking about black holes, more hours contemplating them than any other subject, through countless calculations and fierce debates and sleepless nights. I did this work from a wheelchair, as my body failed year after year, while my mind traveled the cosmos, and black holes taught me something about limits that I carry with me still. The limits of the body are severe and unforgiving, but the limits of understanding are not fixed, because sustained effort and honest inquiry can push them outward. Looking at the night sky means looking at stars, and among them, invisible to any telescope that captures light, are millions of black holes slowly evaporating on timescales beyond comprehension. Each one holds a paradox wrapped in curved space-time, and guards secrets about space and time and information and reality itself. LIGO hears them when they collide as gravitational waves ring across the cosmos, and the Event Horizon Telescope has shown us their shadows, but what lies inside and how information escapes remains hidden from us. The universe has no obligation to make sense to human minds, but it permits us to ask questions, and sometimes when we ask carefully enough and follow the mathematics honestly, even when it leads somewhere disturbing, the universe whispers back an answer. I asked what happens at the edge of a black hole, and the universe told me that the darkness glows. That is what black holes really are. Not dead ends, but doorways. Not the final word of physics, but its most urgent invitation. Not objects from which nothing escapes, but objects from which everything eventually returns to the cosmos, carrying mysteries we have not yet learned to decode. The darkness glows, and in that faint light, if we look carefully enough, the next revolution in physics might already be written and waiting for someone to read it.